Somewhere in Austin, Texas, a small team of engineers is doing something that the semiconductor industry has been trying and failing to do since the 1970s. They're computing with light. Not transmitting data with light, actually computing with it. Doing the matrix multiplications that power every AI model you've ever used, using photons instead of electrons. And in January 2026, Bill Gates, Microsoft, and a coalition of some of the largest energy and industrial investors in the world decided to bet $110 million that they're going to pull it off. Here's why that matters more than almost any chip announcement you'll hear this year. To understand what they are building, you first have to understand the problem nobody in the AI industry wants to say out loud. The AI developers building the biggest models in the world, the ones at the frontier, have been clear. They need roughly 100 times more compute than exists today, not in 20 years. Here's the problem. A modern GPU consumes around 1,200 watts. If you want to make it 100 times faster without changing anything about its fundamental energy efficiency, that chip now draws 120 kilowatts. That's not a chip, that's an industrial furnace. Data centers today are already consuming power comparable to mid-sized cities. 5 gigawatt facilities are being planned, single buildings that would rank among the largest electricity consumers on the planet. Microsoft brought a nuclear plant back online. Google is funding new reactors. These aren't solutions, they're workarounds, because they don't touch the underlying problem. About 90% of what an AI model does during inference, when it's actually answering your question, is matrix multiplication. Multiplying enormous tables of numbers together, billions of times per second. That's the core operation of every transformer, every language model, every image generator. GPUs got good at this because they were originally built for 3D graphics, which also requires heavy matrix math. But as models grew, engineers noticed a fundamental inefficiency. On a GPU, the math happens in one place, the numbers live in another. Connecting them is a memory bus, and crossing that bus trillions of times per second consumes the majority of a GPU's energy. The smartest response was to build bigger systolic arrays, grid architectures that keep data moving locally instead of constantly fetching from memory. Google's TPUs are built around this idea. It helped, but it hit a ceiling. Researchers then tried going analog. An analog array has a beautiful property. Power consumption scales with the perimeter of the array, while throughput scaling with the area. Double the array, roughly double the power draw, but quadruple the compute. The efficiency keeps improving as you scale up, theoretically without bound. But analog electronics have a fatal flaw. Signals slow down as circuits get bigger, because of the RC delays caused by resistors and capacitors. A larger array is more efficient, but also slower. You can't convert the efficiency gain into speed because you've been forced to turn down the clock. The companies that chased analog AI chips in 2018 mostly shut down by 2022. Optical propagation avoids the RC delay limitations electronic circuits run into, and unlike electronic analog arrays, it doesn't degrade with scale, which means an optical analog array gets all the efficiency advantages of analog, power scaling with perimeter, throughput scaling with area, without the speed penalty. You can keep scaling up, and the array gets more efficient and faster simultaneously. This has been theoretically possible since a Stanford professor named Goodman described the first free-space optical matrix multiplier in the 1970s. The physics was always there. The problem was the hardware. To build an optical analog array, you need a dense grid of optical modulators, devices that control light the way a transistor controls current. In conventional silicon photonics, those modulators are enormous. A standard Mach-Zehnder modulator is about 1 millimeter long. In a world where silicon transistors measure just a few nanometers, that's like trying to build a modern computer with vacuum tubes. The arrays you could make were tiny, 64 by 64 elements at most, which meant the performance advantage was almost non-existent. Neurophos's core breakthrough is a new class of modulator they call active metasurfaces. These are programmable reflective surfaces, apply a voltage, and the surface's reflectivity changes, performing the multiplication through physics as the light bounces off. They are approximately 10,000 times smaller than conventional photonic modulators. That's not an incremental improvement. It changes the entire scaling calculation. With modulators that small, you can pack millions of optical processing elements onto a single chip. The architecture folds the Goodman multiplier into a compact 3D stack using beam splitters, co-packaged with standard CMOS electronics and HBM memory, designed to slot into existing data center infrastructure the same way a GPU does. Not a lab experiment, an architecture designed for real data centers. Neurophos's first generation OPU delivers 235p OPS, peta operations per second, at 675 watts at a clock speed of 56 GHz. NVIDIA's best GPU, the B200, delivers 9p OPS at around 1000 watts. That's 26 times more throughput at lower power draw, corresponding to nearly 39 times better energy efficiency per operation. Their roadmap at larger array sizes projects 4228p OPS in a 2-chip configuration, the compute equivalent of roughly 100 GPUs, in the power budget of one. The company has fabricated working metasurface chips. They've demonstrated switching speeds below 1 microsecond. The eye diagrams, the signal integrity tests that tell you whether a device can actually function at speed, are clean. This is not a PowerPoint. The hardware exists. The AI hardware industry has seen this before. Neuromorphic computing, analog AI chips, wafer-scale computing, startups that promised to replace GPUs and disappeared. Meanwhile, NVIDIA kept growing, because good technology isn't the same as winning technology. CUDA, NVIDIA's programming ecosystem, has been built up for over 15 years. An engineer today knows how to program a GPU. Nobody knows how to program an OPU. Hardware challenges are real too. Yield is the graveyard of semiconductor ambition. A device that works at lab scale can fail catastrophically in production. The first integrated OPU is targeted for 2027. Production begins in 2028. The investors, Gates Frontier, Microsoft M12, Aramco Ventures, Bosch Ventures, patient strategic backers, not venture capital chasing a fast exit. History shows the best technology doesn't always win, but when the underlying physics changes fundamentally, when you stop pushing electrons and start using light, the rules can change with it. The energy problem is real. The physics is sound. And someone appears to have found a way to scale compute without scaling the power bill. If that holds up in production, the future of AI may very well be made of light.